Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next few weeks, I will be releasing videos with sample free response questions from each of the 4 AP Physics exams to help students familiarize themselves with what kinds of questions will be asked and how the AP exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, and this video series is intended primarily to help those students. According to AP Central, students can expect to see the following 4 types of questions on the AP Physics 2 exam. There will be 1 question on experimental design, 1 on qualitative to quantitative translation, 1 paragraph argument or paragraph length response, and 1 short answer question. And the question in this video is type number 3, the paragraph argument or paragraph length response. We will be taking a look at 2018 question number 1, which covered electromagnetic induction and electric and magnetic forces and fields. The figures below show a rectangular conducting loop at 3 instants in time. The loop moves at a constant speed v into and through a region of constant uniform magnetic field B directed into the page. The magnetic field is 0 outside the region. Part A. In a coherent paragraph length response, compare the magnitude and direction of the current at times T1, T2, and T3. Include an explanation of why there is or is not a current and the direction of the current if one is present. Use fundamental physics concepts and principles in your explanation. So here we go. According to Faraday's law, a current will be induced when there is a changing magnetic flux within the loop. This occurs while the loop is moving into the region with the magnetic field, such that an increasing area of the loop is filled with the field. That's how I think about it. And this corresponds to times T1 and T2. Since the rate of change of flux is the same at both of those times, due to the constant velocity of the loop, the currents will have the same magnitude. At T3, the flux is no longer changing because the area of the loop filled by the field remains constant as the loop moves through the field, so no current will be induced. And now we need to talk about direction. Lenz's law specifies that the direction of the current will be such that its induced magnetic field opposes the change in flux. With the amount of magnetic field into the page within the loop increasing at T1 and T2, the change in flux is also into the page at both times. The induced field will thus point out of the page, which by the right-hand rule will occur with a counterclockwise current. So before we talk about scoring, note that this looks like a lot of writing, and especially if you've watched the Physics 1 video, there is actually a lot more writing for the Physics 2 exam because the specifications for the paragraph length response that are available on AP Central say that in Physics 1 you can rely on diagrams, graphs, and equations to support your answer, but in Physics 2 you are expected to make less use of that. So now let's talk about scoring. We have 1 point for indicating that the currents at T1 and T2 have equal non-zero magnitudes and are in the same direction. Hold please, I just noticed I wrote T1 and T1, so let me see if I can. Oh, yep, I lose every time I lose my cursor. Let me fix that and make that a T2. Okay, there we go. So the currents at T1 and T2 have equal non-zero magnitudes and are in the same direction. We get a point for indicating that there's no current at T3. We get a point for correctly indicating that the currents depend on the change in flux through the loop or for the forces on the charges moving in the field. We get a point for correctly identifying the direction of the current as counterclockwise and either explaining that the direction of the current generates a magnetic field that opposes the change in flux, or analyzing the force on the charge carriers in each segment of the loop. That's like emotional EMF kind of approach. And then our last point is for an on-topic response that has sufficient paragraph structure as described in the published requirements for the paragraph length response. Part B, the loop is removed. A proton traveling to the right in the plane of the page as shown below then enters the region of magnetic field with speed v equals 3 times 10 to the 5th meters per second. The magnitude of the field is 0.03 teslas, and the effects of gravity are negligible. Part 1, calculate the magnitude of the force on the proton as it enters the field. So we're going to need to recall the equation for, for the magnetic force on a moving charge. And that is going to be Q V B sine theta, where theta is the angle between the velocity and the magnetic field, which in this case is 90 degrees, because our velocity was coming in perpendicular to the field. So we can just go ahead and substitute. The charge on a proton is 1.6 times 10 to the negative 19th coulombs. Our velocity was 3.0 times 10 to the 5th meters per second. Our magnetic field strength was that 0.030 teslas. And of course, like I just said, sine of 90 degrees. And so that's going to give us a value of 1.4 times 10 to the negative 15th newtons. And this part was worth only 1 point, and that 1 point is for correct substitution into a correct expression and correct units on the final answer. Part 2, on the figure below, sketch a possible path of the proton as it travels through the magnetic field. Clearly label the path P1. Well, recall that the magnetic force is perpendicular to both the velocity and the magnetic field, so we can apply the right-hand rule. Part of this is going to look a little backward for you, so I'm going to put all of my fingers in the direction of the proton velocity. I like to leave my first 2 fingers in the direction of the velocity, and then I'm going to curl my 3rd and 4th fingers into the page for the magnetic field. That, of course, looks like out of the page for you, but when you curl into the page for you, it's going to look like you're pointing at me. And then, of course, my thumb comes up for the magnetic force at that point of entry. So our proton is going to path that curls upward or curves upward like so. And our points here are a point for drawing a curved arc through the field, curved upward where the proton enters. And there was a note that anything greater than a semicircle or a path that does not reach the edge of the field does not earn credit. Any path after exiting the field is ignored. And now in part 3, a second proton now enters the magnetic field at the same point and from the same direction but at a greater speed than the first proton. On the figure above, draw the path of the second proton as it travels through the field. Clearly label the path P2. Well, we're going to need to think about, to figure out what that path is going to look like, the fact that our magnetic force is going to be providing a centripetal force. So centripetal force is mv squared over r. That's going to be equal to qvb, and I'll leave off the sine theta because it's 90 degrees, so it's just going to be 1 QVB. And so notice that one of the powers of V on the left will cancel out with a power of, well, the only power of B on the right. And now when I rearrange this for R, I'm going to get MV over QB. So we can see that as the velocity of the particle entering the magnetic field increases, so too does the radius of its path. So our path P2 will look like this. And our points here are for, or single point, is for drawing a path with a larger radius that's consistent with the answer to B part 2. So what that means is if you had drawn path P1 curving downward, as long as you drew a larger radius for path P2, you can still get credit for path P2, even though your original path P1 was wrong. And that's really common across all of the AP Physics exams, that if you have to base a later answer or like carry an earlier answer through, and that earlier answer is wrong, then they only ding you once for the first mistake and not every time the mistake gets propagated through your future work. Part 4, next, an electric field is applied in the same region as the magnetic field, such that there is no net force on the first proton as it enters the region. Calculate the magnitude and indicate the direction of the electric field relative to the coordinate system shown in Part B. So let's start with the magnitude, and then I'll refresh that coordinate system for you. So we are experiencing no net force. So that tells us that our electric force must be exactly balancing our magnetic force. Well, how do we calculate the electric force on a moving charge? With its charge times the electric field strength. And of course, our magnetic force is QVB. I am actually going to go ahead, even though I already calculated that force in a previous part, I'm going to go ahead and keep working this as if I hadn't, and notice that the amount of charge is going to cancel. And so I'm left with my electric field will just be equal to the velocity times the magnetic field strength. So I can now substitute 3.0 times 10 to the 5th multiplied by that 0.030 Tesla's magnetic field, and I get an electric field strength of 9,000 newtons per coulomb. And so, quick reminder that this was the coordinate system shown in Part B, with positive x to the right, positive y up, and positive z out of the page. And so we need to specify a direction now for our electric field. We've got two ways we can think about it. Actually, there's really only one way we need to think about it, which is that since at the point of entry, the force was up on the proton from the magnetic field, if there's no net force, then the electric force must be downward, which is the negative y direction. So you could specify in the negative y direction, or you could say toward the bottom of the page. Okay, and now scoring. This is another situation where I'm going to spend more time writing about the scoring than I did actually solving the question. So we're going to get a point for equating the electric and magnetic forces. I can't even point to a particular place where this is most appropriately applied. So because there's more that you have to get this point than just equating the electric and magnetic forces. And for substitution, into the correct expression, using values consistent with the response to part B1. So what that means is, like I said when I was solving it, I could have just used my magnetic force value instead of setting it equal to QVB again here. And that would have also been fine as algebra-wise. And then our last point is for indicating a direction of the electric field. Consistent with the response to part B1. So again, if for some reason, sorry, B1 or B2? Actually, I think that's supposed to be B part 2. Because again, if you incorrectly thought that the force on the proton would be downward from the magnetic field, and you'd drawn a curved part downward in B part 2, then you might think that the electric force would be upward now for there to be no net force. So again, this is another situation where you can still get full credit if a later answer is based on an earlier answer that you happened to have made a mistake in getting. So I hope you have found this presentation of a paragraph length response question for AP Physics 2 helpful. If you have a video solution request from my YouTube channel, you can send it to physicsproblemrequests@gmail.com. If you need some email assistance, you can send your problem and the work you've done on it so far to freephysicshelpline@gmail.com. There's a limit of 10 questions per academic year. If you'd like to learn more about my online physics tutoring services, you can email me at brandyhaflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the links shown here for the AP Physics 2 exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.